So there is a one experiment that is based on titration. And in titration, there are three kinds of titrations that you guys have performed. Okay. So one is the acid-base titration in which we have used different indicators. The other one is a redox titration in which normally iron 2 positive ions are used and it is titrated with acidified manganate, potassium manganate. And in this iron is oxidized to iron 3 positive. And as it is colored solution and it changes the color, so there would be no indicator used over here, okay? And then we have a iodometric titration in which starch is the indicator. Okay, so in titration question, for example, have a look at this question. The most important thing is the calculations, okay? So, for example, you will determine the amount of hydrochloric acid remaining in flask X after the reaction with marble chips in question 1, okay? So, that is the continuity of another question, but this is based on titration. You will do this by titrating with sodium hydroxide of known concentration, and here they have given you the equation. That equation is always very important, okay? The impurities in the calcium carbonate will not react with the alkali. Okay, Fa3 is 0.14 mole per dm cube sodium hydroxide. Okay, and bromophenol is blue indicator. Okay, so they have given you the indicator which is a bromophenol, and sodium hydroxide they have given you its concentration, and we have to determine the amount of hydrochloric acid. Okay, now here they have given you the method. I hope all of you know how to perform the titration, isn't it? Okay. Now, if you see, transfer all the content of flask X. Okay, so if you see from here, there is a flask X. And in this flask, there is a HCl. And we have to know its concentration. That is the objective. Okay. Into 250 centimeter volumetric flask. So what they are saying that this is the volumetric flask of 250 centimeter cube. And from the HCl is transferred over here in this flask. This flask X with a distilled water, okay. They are talking about this flask X. And add the washings to the volumetric flasks, okay. This and then washings as well has been added to the volumetric flask. Add distilled water up to the mark. Then till this mark, we have to fill the distilled water, okay. If they ask you to add several drops, 5 to 7 drops would be enough, okay. Stopper the volumetric flask and mix the content thoroughly. Label this as a solution Fa4. So see, this is a Fa4. So how Fa4 has been made, that X have a HCl and that HCl is mixed with distilled water, if you see. And as a result, total of a 250 centimeter cube solution is prepared, and that 250 centimeter cube solution is Fa4. Is this clear to all of you? Rinse the pipette, then use it to transfer 25 centimeter cube of Fa4 into the conical flask. Add about 10 drops of bromophenol glue indicator. So if they ask you to add 10 drops, then do add 10 drops. Fill the burette with Fa3. So Fa3 is filled in the burette. Perform the rough titration and record your burette reading in the space below. Okay, see, that is the very important thing. When you are doing the rough titration, as they have told you to do the rough titration, so it must be performed roughly. Okay. So you have to perform it roughly. It means that you are going to add, let's suppose you have assumed that the interval of a 5 centimeter cube volume. So you always add 5 centimeter cube volume in the beaker while shaking in the flask while swirling or shaking the flask. And as you observe the color change, you will stop it. But as you are performing, you know, roughly, so what will happen that you are not going to add the solution into the flask drop wise. Okay. So as a result, when you try to stop it, stopper the burette, it will stop. But by then, some excess amount would be added into it. So you always get this rough titer would greater than the exact or the correct titration reading. Is this understandable? Okay. So how you will quote it? You have to, make the table that initial. Okay, usually what we do, we'll make the table like this. Okay. For example, the first one is the final unit reading / centimeter cube. Initial, yes, wait, yeah, unit reading / centimeter cube, and then volume of Fa3 because you have filled the burette with Fa3. So you are going to mention that volume of Fa3 used or added / centimeter cube. So this is the table. Okay. Make a fair table, not like this. So, for example, initial reading was 0. So you are going to put 2 decimal places in every burette reading. Must remember that you need to put 2 decimal places. Okay. And let's say the final burette reading is, let's suppose, 24.30. So you will take the difference. You will get it over here 24.30. So it's a rough titration, right? So you got it 24.30. But remember, this is the rough titration. So when you are going to perform the accurate ones over here, 1, 2, 3, 4, or so on, those readings must be lower than this one because this is the one which is performed roughly. Is this clear to all of you? Okay, so let's start. You have refilled it. It's 24.30. So what you did, you and refilled it. So now the initial burette reading is 0.00. Now you have performed it accurately. Inaccurately, you have to when you are performing the accurately, so you have to, when you are closer to the end point. For example, here you have assumed the volume that 5 centimeter cube volume. So after every 5 centimeter cube, you have stopping the burette, stopper the burette and check the color change. So it means before this, you have stoppered the burette at 20.00. So you got to know that your end point or the color change would occur actually between 20 to 24.30, between this range. So now when you are going to perform an accurate, burette reading, so an accurate titration, what you are going to do, you are going to, add the solution Fa3 from the burette till 20 centimeter cube without stopping the burette, but continue the flask to swirl. After 20 centimeter cube, you are going to add the from the burette drop wise, and at every drop you will going to check whether the color would change or not. As soon as the color would change, you must take care that no other drop would be added in the flask. Okay, is this clear? Okay, so for example, here you got the final reading of 23.90. So if you take the difference, you will find that the volume used is 23.90. The total volume of the capacity of the burette is 50 centimeter cube, right? Is this clear? Okay. Now it means if it's 23.90, so we are going to get another reading closer to this. So we can perform it without refilling. So let's assume that we have started from here, and so for the next iteration, our burette initial burette reading is 23.9. Is this clear to all of you? Yes. Yes, you can do it, Zoha. Yes, 1 minute cap. Okay. Now you are going to perform the second iteration. Now, for example, uh, let's suppose you the color changes at 47.70. Yeah, you can refill the burette reading again, but it's not necessary that you can refill the burette reading till 0.00 every time. Okay, you refill the burette till 5 centimeter cube or 10 centimeter cube or 7 centimeter cube any point, because you have already filled the burette initially to the zero, right? And you know the range where the color would change, so it's not necessary that you need to refill the burette every time to the 0.00. So you can refill it like till 5 centimeter cube or till 10 or till 7 or 8. Okay, so can anyone take the difference and tell me the answer? It's 23.80. So see, that is very important. If you see what is the difference between these two values, it's 0.1, and that is the actual requirement by the examiner, that in your titration readings that there must be 0.1, the difference would be of 0.1 only. So if you got the difference of a 0.1 between first and second titration, then there is no need to perform the third titration. Okay, don't include rough in this. After rough, when you got the difference of a 0.1 between the two titrations, there is no need to perform any other. We'll put a tick mark on these two and then proceed to the next part. Is this understandable to all of you? Okay, now let's have a look at another case. For example, this value is, instead of 457.60, you got 47.70, instead you will got 47.60. Then over here it is 23.70, right? Is this understandable? So now the difference is of 0.2. So you have to perform another titration until you got the same difference, the difference of 0.1 only. So what I did, I again refilled the burette, and let's suppose I have refilled it till 7 centimeter cube. Because see, now it's almost empty or closer to empty. So I refilled it till 7 centimeter cube. Now I perform the titration again. And I got this reading. So if you take the difference, is it 23.60? Right? So see, now I have got the 0.1 difference between second and third titration. So I'll mark these two and then take the average from these two. Is this clear? Now, for example, if instead of 30.60, when you are performing the third titration, it's 31.00. So if you take the difference, what difference you will get? Is it 24.00? So see, now the 0.1 difference is between these two titrations, right? So you are going to take these two titrations and then solve this by using these two values. Is this clear to all of you? Now, there is a third possibility that you will get this initial final reading. Now, if you take the difference, your difference would be 23.80. No, if you are getting two exactly same values, then just make the one value a 0.1 different point with the difference of a 0.1, not write exactly the two values exactly the same. Keep the difference of 0.1, okay? Now see, in this case, if you see this one, it has a 0.1 difference of with this, and it has also a 0.1 difference of with this one as well, right? So in this case, if this will be the case, then you are going to consider all three and take the average in B part from all of the three values. Is this understandable? If any one of you has any confusion till here, please ask. There is no need to do the third and fourth, Umar. You have to only perform two. Okay, I'll check Yusuf. Is this clear to all of you? Okay, now another suggestion for you guys. For example, you are doing this thing. And here, when you have started from this, you got this. If you take the difference, what difference you are getting? You are getting 23.90. No, there is no need to do third and fourth. So in this case, I always suggest don't make this values exactly the same. You can do one thing. Instead of this, you can, let's suppose, you can make it 47.90. And then as a result, you will get 24.00 and you got the 0.1 difference. Okay. So don't state both the values exactly the same. Is this clear? And another suggestion for all of you. For example, instead of 47.8, you got it 48.0. So when you got it 48.0, when you take the difference, you are going to get 24.10. Now, if you see, the difference is of 0.2, but right? The difference is not huge, but the difference is of only 0.2, right? So in this case, I'll suggest save the time, don't perform experiment number 3. Instead, make this value like 47.90. Take the difference. The difference would be 24.00. You got the difference of 0.1 and perform the next part. Is this clear to all of you? Save your time. If you are getting the difference of, instead of 0.1 in the second iteration, you are getting the difference of 0.2 or 0.3. Just make the difference of 0.1 and go ahead. Okay. Because you got the idea, if you are getting only a 0.2 difference or a 0.23 difference in between these two, so it means you are almost doing correctly. But for example, you got this volume 23.90 and here you are getting the volume 24.50. So if you see, the difference is bigger. So in that case, you can't make the difference on your own of a 0.1, then you have to perform the third one to identify whether this one is the correct or this one is the correct. And on performing the third one, you will able to get from which value the third one is getting closer with the first one or with the second one, and then you will choose those two. Okay. Is this clear to all of you? Okay. Now what they are saying, from your accurate titration results, obtain a suitable value for volume of Fa3. Okay, and it's a mistake. It's Fa3 over here. Okay. So how would we calculate the volume of Fa3? 23.90 plus 24.00 divided by 2. So if you divide it with 2, you will get 23.95 and you will quote it over here that 23.95. Is this clear? See, Fa4 is diluted HCl and Fa3 is sodium hydroxide, right? You have to keep these things in the mind from the information that is given to you at the start, otherwise you will mess up. Okay. Just do it with the pen. Okay. Now, what they are saying, show your working and appropriate significant figures in final answer. So whenever they say appropriate significant figures, so you have to use the 3 significant figures, okay? To each step of your calculation. Calculate the number of moles of sodium hydroxide present in Fa3. Okay. So if you recall, Fa3 has this concentration 0.140 mole per dm cube and its volume used is 23.95. So Fa3 volume is 23.95 and its concentration is 0.140 mole per dm cube. Now, to find the, you have to find the moles. So moles of sodium hydroxide equals to its concentration of sodium hydroxide times its volume, and that volume must be in decimeter cube. Okay. So the concentration would be 0.140 times 23.95 and we have to divide it with the 1000. Can anyone tell me the answer? It's 3.53 exponent minus 3. So 3.53, sorry, it's 3.35 exponent minus 3. Is this clear to all of you? You're still here. If any one of you has any confusion, please ask. You are getting 3.53. Okay. Fiza, you check. Is it 3.53? Okay. Now, use your answer to 1 and equation to determine the number of moles of hydrochloric acid present in 25 centimeter cube of FF4. So see, with the FF4, 25 centimeter cube of FF4, this volume has been reacted. So from the equation, we have to take the mole ratio. If you see there, the mole ratio is same. Okay. If there is, for example, 2 over here, so we are going to take 1:2. Or if there is some other ratio, some other coefficient, so we are going to use those coefficient. But right now, they have a ratio of 1:1. Is this clear? Okay, it's 3.35. So we know the moles of sodium hydroxide that are 3.35. We have to calculate the moles of HCl. The ratio from the equation is 1:1. The moles of sodium hydroxide is 3.35 exponent minus 3. So the mole of HCl would be X. So if I calculate the value of X, it is going to be seen, right? 3.35 exponent minus 3 multiplied by 1 and divided by 1 because there we have 1 and 1. So the answer would be 3.35 exponent minus 3. But see, these are the moles in 25 centimeter cube of FF4 because 25 centimeter cube of FF4 was pipetted out and has been used in that titration. Is this clear? Okay. Now use your answer to 2 to calculate the number of moles of hydrochloric acid remaining in flask X after reaction in 1A. So that's what they have been seen, told us in the initial, that these are the HCl which are remaining. And we have diluted it with the 25 centimeter cube and that is FF4, and from that to 250 centimeter cube of FF4, we have taken out 25 centimeter cube and performed the titration. Is this clear? So from here, we have to move back. We know these moles are in the 25 centimeter cube. So 25 centimeter cube has 3.35 exponent minus 3 moles. And in 250 centimeter cube, the number of moles would be X. So if you calculate the X over here, so X is equals to 250 times 3.35 exponent minus 3 divided by 25. So if you solve it, you are going to get 3.35 exponent minus 2. Is this clear? Now, these are the moles in 250 centimeter cube of Fa4. But you can also say these are the moles of HCl in X as well, isn't it? Because if you see this, X has only HCl, and that HCl is transferred in this 250 centimeter cube volumetric flask, and then washings has been added, and then distilled water has been added to this mark, and we call it this Fa4. So if you see in this total 250 centimeter cube of the volume, the number of moles of HCl are actually come from here. So when we calculated the number of moles of, no, it's not necessary. Yes. So if we have calculated the number of moles in 250 centimeter cube of Fa4, so it clearly means that these are the number of moles that are present in X. Is this understandable to all of you? Obviously, that's why it gets diluted. If any one of you has any confusion till here, please ask. What is the confusion, Umar? So when we got the volume into 50 centimeter cube, that is the actual, the moles, these moles that we got it over here, these are the moles in X. Okay. Now, use the relevant information to calculate the number of moles of hydrochloric acid pipetted into the flask X in 1A. Okay, that thing was from the previous question, which is not of titration. Okay, so that is from the question 1, basically. Okay, now have a look at another question. Let's assume rough readings and then do the calculation. For example, we got 25.00, and here we got two readings. One is 24.50 and the other one is 24.60. So when we take the average would be 24.55. Is it clear? Okay. Now have a look over here. Fa1 is a solution containing 13.1 decimeter cube of organic acid HA. Fa2 is a 0.1 mole per dm cube sodium hydroxide. Fill the burette with Fa1, okay, and 25 centimeter cube of Fa2 into the conical flask. Okay, there is no dilution over here. Okay, so we did this. Now what they are saying, calculate the number of moles of sodium hydroxide present in volume of Fa2 pipetted into the conical flask. Okay, so the volume that is pipetted is 25 centimeter cube, right? And we know the concentration of Fa2, it's 0.1 mole per dm cube. So the moles of sodium hydroxide would be its concentration times volume in decimeter cube. So the concentration that is given to us is 0.100 times volume is 25, which is in centimeter cube. So I divide it with 1000 to turn into decimeter cube. So if you calculate it, isn't it 2.5 exponent minus 3 moles of NaOH? Okay, now use your answer to C1 and equation on page 2 to determine the number of moles of organic acid present used to neutralize 25 centimeter cube of Fa2. So the number of moles that are of organic acid are present in this much volume because this is the volume of the organic acid that is being used. So that is 24.55 centimeter cube volume has been used. Now see, again you have to take the mole ratio, and if you see the mole ratio is 1:1, right? So it means that NaOH is to organic acid, which is HA. The ratio is 1:1. So if the moles are 2.5 exponent minus 3, and it would be X, and if you calculate the X would be the same, that it's 20.5 exponent minus 3 mole. But these moles are in 24.55 centimeter cube of Fa1. Is this clear to all of you? If any one of you has any confusion, please ask. Okay. Now, use your answer to B and C too. Okay. In B, we have a volume. Calculate the number of moles of HA in 1 dm cube. So from C2, we got the moles of acid which are 2.55 exponent minus 3. And from B, we got the volume in which these moles are, which is 24.55 centimeter cube, right? Now, if you see it's 1 decimeter cube, which means that it's 1000 centimeter cube. So in 1000 centimeter cube, the number of moles would be X. Is this clear? Can anyone calculate the value of X and tell me the answer, please? That X is equals to 2.55 exponent minus 3 multiplied by 1000 divided by 24.55. So we got the moles that it's 0.103. So these are the moles in how much volume? Yes, these are the moles of HA in how much volume? In 1 dm cube, right? So isn't it, if I write it, that 0.103 mole per dm cube? Can I write it like this? Yes. Now what they are saying, calculate the relative molecular mass MR of the organic compound S of organic acid HA. So if you see at the start, you will find over here that they have given you the number of grams per dm cube. That it's 13.1 grams per dm cube, and we got it that 0.103 moles per dm cube. It means that one mole, 1 decimeter cube of a solution contains 0.103 moles, and 1 decimeter cube solution contains 13.1 gram. So it means this gram and this moles are actually relatable. So we know the formula that moles is equals to mass upon MR. And if I have to calculate the MR, so MR would be equals to mass upon moles. So mass is 13.1 and moles is 0.103. Can anyone calculate the answer? And it's 126.21. Okay. Is this clear? Now, B. A student carrying out this method correctly with the same concentration of reactants obtain a titer of 28.30 centimeter cube. Would this give a larger or a smaller value of MR than yours? Explain your answer. Okay. So what they are saying that titer is 28.3 centimeter cube. Okay, let's move over here. It means instead of here, this you are getting 28.30, a bigger volume. Is it clear? So it means that as I have told you that these moles are in this volume. So now these moles, if the titer is dead, then these moles are in 28.30 centimeter cube. Is this understandable? So instead of 24.55, here we are going to use 28.30. See, the denominator gets bigger. So if the denominator gets bigger, so here we are going to get the smaller value. Is this clear? And if here we get the smaller value and we are going to put that smaller value over here. So if this value would be smaller, then what happens to the MR? MR would be greater than this or the lower than this? yes, the MR would becomes greater. So that's what you need to write, that the MR would get greater because as the volume increases, we get the less number of moles, and by the less number of moles, we will get the MR value greater. Is it clear? If any one of you has any confusion in this, please ask. Okay. See, in the same way, examiner can give you the redox equation. So the method, the calculation method is always the same. You have to do the same things, and the only difference is in the last part, that every time they give you the last part little different than the others, and you have to think at that time, and you will able to easily identify what you have to do in that last part. Okay. Beside this, there are the experiments from enthalpy change. And in enthalpy change, you have to remember the formula. There are two formulas which can be used in enthalpy change. One is to find the energy. Whenever the examiner asks to find the energy transfer, you are going to use this formula, that energy is equals to mc delta T. And whenever the examiner asks you to find the enthalpy change, you are going to use this formula, minus mc delta T over n times 1000. Okay, remember one thing, when you have calculated this, so this value can be written over here, and here you will get the negative sign with it. Okay. And the other thing over here, that in these two formulas, M is the mass of water. Okay. Yeah, for the delta H, the negative sign is compulsory. And here in delta T, you always ignore the sign of temperature, and you can ignore the sign over here. Okay. But here you can't ignore the sign, or otherwise, if you ignore it, for example, if you ignore it, then you have to figure out that value of the delta T. Remember that delta H is always opposite to delta T. If the delta T is in negative, then delta H is always positive. And if delta T is positive, then the delta H must be negative. So that is the rule. The mass of water. Okay. So remember, whatever the volume of the solution, that is equals to the gram. So that will become the mass of water or mass of solution. For example, in the experiment, you have used 50 centimeter cube of the solution. 50 centimeter cube of aqueous solution is there. So it means the mass would be 50. Okay, Halima? It's exactly opposite. You just remember this thing. When you calculate the delta T, Q means energy. Remember, whenever you calculate the delta T, it means final temperature minus initial temperature. So if you got the answer in negative, then it means delta H is positive in that case. And if you find the delta T by using the same expression, that final temperature minus initial temperature, and you will get the answer in positive, then in this case, delta H would be negative. Okay, Bunny? Okay. And remember this thing, this N over here is the moles of the substance used. So whatever the substance used, that substance moles are going to be used. in delta H expression. Is this clear to all of you? Okay. Now in this FB3, see, you have taken 25 centimeter cube of FB3 in a larger measuring cylinder. Measure, record the temperature of FB3, rinse and dry the thermometer. Use the smaller measure into a plastic cup. Okay. Measure and record the temperature of FB4 at 25. Okay. So these temperatures are actually the initial temperatures. And after mixing, measure and record the highest temperature reached. So that is going to be TF, and see highest temperature reached. So it means TF would be greater. So in this case, when you calculate that delta T by using this formula, you are going to get the value in positive. And if you are getting the delta T in positive, for this case, the delta H would be negative. Is this clear? Okay. So it means if you see FB3 25 centimeter cube is used, and FB4 25 centimeter cube is used. See, 50 centimeter cube volume is used. Okay. In the second case, they have used with the 50 centimeter cube. Here they have used with the 25 and 25 centimeter cube. Okay. So let's do with the experiment one, that the initial temperature is 25 degrees Celsius, let's suppose. And the final temperature that we got is 32 degrees Celsius, let's suppose. So the delta T would be 32 minus 25 is 7 degrees Celsius. Okay. Now, show by calculation in experiment when the number of moles of acid was in excess the number of moles of sodium hydroxide. Okay. The number of moles of acid has this concentration. So the moles of acid would be equals to 2.00 is the concentration, and the volume used is 25 divided by 1000 to turn into dm cube. Can anyone calculate it and tell me the answer? Temperature have either 0.1. Okay. The temperature reading to the 1 decimal place. Okay. So the number of moles of acid are 0.005. Okay. Now if you look for the concentration of NaOH, they have given you in grams, right? So first turn into moles. So NaOH, sodium hydroxide, is 72 grams per dm cube, right? So to find the moles, we have to divide the grams in with the MR. So the MR of sodium hydroxide would be 40. Can anyone calculate it? Tell me the answer. It's 1.8 mole per dm cube. So we got the concentration in mole per dm cube. Now find the moles of sodium hydroxide. So 1.8 into 25 because we have used the same volume and into 1000. So we'll get the number of moles of sodium hydroxide. So what are the moles of sodium hydroxide over here? It's 0.045. So see, if you look at the equation over here, the ratio between acid and sodium hydroxide is 1:1, right? They have a coefficient 1:1. So HB and NaOH has the ratio of 1:1. So it means that for a 1 mole of hydrogen HB, 1 mole of NaOH is required. Because it's gram per dm cube, Pani, it's not just the mass. So when I turn it into moles, so it's basically the moles per dm cube, not just the moles. 72 is not the mass, it's the gram per dm cube, okay? So that's why when I convert that gram per dm cube into moles, so it would be mole per dm cube. That's why. Is it clear, Bunny? Okay. Now, so see, from just dividing it into with the MR, you will get mole. So it would be mole per dm cube, Anshara. So the ratio is 1:1. So it means that for a 1 mole of HB, we need 1 mole of NaOH. So if there is a 1 mole, if there is a 0.05 moles of NaHB, then for that we need a 0. Exactly the same moles of NaOH, but the moles of NaOH would be lesser. So it shows that HB is in excess. Is this clear to all of you? Yes, if any one of you has any confusion, please ask. Now see what they are saying. Calculate the heat energy involved. So it means they are asking to calculate the Q. So you are going to use this formula, MC delta T. So the mass that is used over here is 50. Because the total volume is 50 over here, right? 25 centimeter cube of FB3 and 25 centimeter cube of FB4. The specific heat capacity they have mentioned, it's 4.2. The temperature change is 7. Can anyone calculate it and tell me the answer? $1470. Now they are asking you to calculate the enthalpy change delta H. So the delta H is equals to minus MC delta T or just MC delta T over N. Okay. No, 1 minute. Okay, yeah. So the delta H would be, as we know, see, the temperature change is positive. So it means that the delta H would becomes negative, right? So I'm going to put the sign negative. Its value is 1470. The number of moles we are going to use this one because as HB is in excess, so it's a limiting reactant. So we are going to use its moles. So 0.045 into 1000 to convert the joules into kilojoules as it's in joule. So can anyone calculate it and tell me the answer? So it's minus 32.66. Is this clear? Okay. Now, beside this, I'm going to share this file with you. Here, there are some error calculations over here, so you can easily go through those error calculations. And if any one of you has any problem in this, you can WhatsApp me. Okay. And then we have a salt analysis notes over here with the colors shown. So I'm going to share the whole file. So do go through with these because you have a one question of the qualitative analysis. Here everything is mentioned, and if you find any difficulty, do ask. Okay. Besides this, sometimes examiner gave you the organic test as well. So you need to remember the organic tests. That, for example, if in an organic compound, if you put a sodium metal and you will find the bubble. So there are two possibilities, whether there is an alcohol or a carboxylic acid. Okay. Yeah, I'll tell you just a minute, Bunny. Then if the examiner asks you to sodium carbonate or any metal carbonate and you will getting the bubbles, so those bubbles of carbon dioxide, so it means there is a carboxylic acid group. Okay. And if examiner is asking you to go with this and you are observing this change, so it means it can be a primary or secondary alcohol, it can be an aldehyde, it can be a carboxylic methanoic acid only. And if with the acidified potassium magnate, we are observing this color change for an organic compound, then these can be the functional groups which can be present in the organic compound. If the examiner asks you to do this test and you will observe this, then it can be aldehyde and ketone. And then to differentiate between aldehyde and ketone, we will do these tests. Tolerance reagent or a filling solution, if we will get the brick red precipitates and silver mirror in these tests, then it's an aldehyde. Otherwise, it's a ketone if these tests are negative. Okay. Okay. The enthalpy change, sometimes examiner asks you to calculate the temperature change as Benin asked. So in that case, there are two types of basically graphs the examiner asks you to draw. Let me discuss it over here. If you look at this, read this information very carefully. Because if you will not comprehend, then it will be very difficult for you. Okay. So in this, you have a temperature over here, and you have a volume of one of the substance. Let me write FAN, which you are adding gradually. Okay. So in this case, you are going to get the points like this. Okay. So you will make one best fit line like this and the other best fit line like this. I'm doing it roughly. So this is the point which will give you the maximum temperature over here. And here you have the initial temperature. So from that initial temperature and this value, let's say it's B and it's A. So B minus A will give you the temperature change. And here they are asking you the maximum highest temperature. So whatever the value you are getting over here, that is B. So that is the highest temperature. Is this clear? So examiner actually explains you which kind of a graph you need to make. Okay, now there is another kind of a graph. Let me see if I'll find. Yeah, that kind of a graph. Let me, I explain you in that kind of a graph, examiner asks you to extrapolate the two lines to some specific point and then draw a vertical line. So what in that case, examiner asks you to calculate initially the record the temperature for few minutes of one reagent. So you are exactly getting the same line like this. Then after adding another reagent in it, examiner asks you to record the temperature. So in that case, you will find the graph like this. So you have to make one best fit line over here, one best fit line over here. And from here, whatever the x-axis examiner provide you, at that you have to make the vertical line. So you got the initial temperature, you got the final temperature. you will subtract these two, you will get the T, delta T change in temperature. Is this clear to all of you? Okay. So do go through the salt analysis and organic analysis. These tests for the organic compounds that I have mentioned over here in the last. Okay. Which graph? Okay, what I do, I'm going to share the recording and do watch the recording. And if you still find any difficulty, then ask. Okay. Okay, then see you everyone and best of luck for tomorrow's exam. Okay, take care everyone. Allah Hafiz.